Okay, we've talked about some reactions that alcohols can undergo, a set of elimination and substitution reactions, dehydrations, formation of alkyl halides. The next set of reactions that we're going to look at for alcohols are oxidation reactions. Now, this is going to be the opposite of what we saw when we were making alcohols. If you remember in our previous discussion, we were making alcohols based on the theory that if we had ketones or aldehydes or esters or carboxylic acids, we could use reducing agents to turn them into alcohols. Now we're going to take alcohols and use oxidizing agents in order to turn them into those other functional groups. And we need to consider a little bit about what type of alcohol we're looking at. So if we have a primary alcohol, let's draw one out here, right? A nice simple primary alcohol. We can imagine we could oxidize this into different functional groups. Maybe we could turn it into, let's say an aldehyde, right? It's important in these to count your carbons to make sure you're not adding or subtracting carbons. Or we could, oxidize this even further, right? Not adding any more carbons, but, adding 3 carbon-oxygen bonds to turn it into a carboxylic acid, okay? We wouldn't imagine we'd be able to do a ketone because that would either require us to add another carbon. Well, that would require us to add another carbon, and that's not a strict oxidation reaction. So there are different reagents that can be used on primary alcohols to either oxidize them all the way to carboxylic acids or to oxidize them partway to an aldehyde. One useful reagent that's used on primary alcohols is our PCC, pyridinium chlorochromate reagent. It's not that reactive as an oxidizing agent, and while it's able to oxidize primary alcohols, it can only oxidize them to this state, to the aldehyde state. It can't oxidize them all the way to carboxylic acids. Now, reagents like chromium trioxide are really good at oxidizing all the way to carboxylic acid. We'll look at the mechanism for how this oxidation works, and they all sort of work in a kind of similar manner, doing an elimination reaction to generate this carbon-oxygen double bond. But we'll stop here for this discussion right now. Now, with secondary alcohols, let's just write out a secondary alcohol and try to think about what we might be able to do with that. Here's a secondary alcohol, right? Our 2-propanol. If we oxidize this, what could happen? Well, we're not going to be able to go all the way to the carboxylic acid, right? This oxygen's stuck right in the middle of the molecule, and carboxylic acids aren't in the middle of the molecule. They have to be at the end. We're not going to be able to oxidize it to an aldehyde either. These are terminal functional groups, and by having a secondary alcohol, this carbon-oxygen bond's stuck right in the middle. So what do you think we're going to be able to oxidize this to? Well, without adding any carbons, really our only option for oxidation is to keep that oxygen where it is, just turn it into a carbonyl group. So secondary alcohols oxidize really well to form ketones, and we need a pretty decent oxidizing agent. Our sodium dichromate is pretty easy to use and can oxidize secondary alcohols to ketones. Okay, what about tertiary alcohols? How are we going to oxidize those? Well, I can't, right? We can't add any more carbon-oxygen bonds here because this carbon is saturated with carbon-carbon bonds. So we can't oxidize tertiary alcohols any further. And if we treat them with any of these oxidizing agents, they don't work. It's not reactive. Okay, so let's look at a mechanism for how these chromate or chromium-based oxidizing agents work. We'll take our chromium trioxide and look at its basic mechanism. You're not responsible for knowing this mechanism, but it is kind of useful just in theory to know that there is a mechanism, and these aren't just magical reagents. Again, we have some molecule or some atom in the center of these electronegative atoms that becomes partially positive charge, and the alcohol group can act as a nucleophile to attack it. Electrons go out to form our light bulb, and in this case we get what looks like to be a decent elimination E2 based reaction, where we get a double bond forming between the carbon and the oxygen on our substrate. Okay. So this is the type of E2 based mechanism that these chromium based reagents do in order to generate more carbon oxygen bonds in them. And it's important really to remember this PCC. It's very handy to take these primary alcohols and to oxidize them and stopping at this aldehyde group instead of oxidizing all the way to the carboxylic acid.